Good evening. Welcome to the public lecture organized by the Institute for Mathematical Sciences. My name is Untitled. I'm the director of the Institute. This evening, we are very happy to have as our speaker Professor Tamás Hausel. He was born in Hungary and studied in Hungary and also received his PhD from the University of Cambridge. And after the PhD, he spent a few years at the Institute for Advanced Study in Princeton, followed by a Miller Fellowship at Berkeley. And then after that, he joined the University of Texas at Austin to be an assistant professor and then subsequently associate professor. And then after that, Professor Hausel went to England. He took up the Royal Society University Research Fellowship, I believe, at the Mathematical Institute, University of Oxford. And during that period, he did extremely well, received the prestigious Whitehead Prize from the London Mathematical Society. In 2012, Professor Hausel joined the École Polytechnique in Lausanne, where he is now head of the chair of geometry at that university. We are very happy that he is able to participate in a workshop that is in the program, ongoing program on Higgs bundle. And this evening he will give us a talk on what is called the magical pictures of Higgs bundles. Please welcome Professor Hausel.
Thank you very much for the visitor. So thank you very much for this introduction and also for the whole program and then it is really a pleasure to give this lecture here. So what I'm going to talk about basically two things at the same time. One will be first introducing you these ideas of magic pictures, something which I really like, that sort of puzzles I really liked when I was school children. And then I will explain to you how you can find such magic pictures in the subjects of Higgs bundles. So Higgs bundles are the focus of this workshop or this program we have at the Institute for Mathematical Sciences. And I will also say a few words about those. Okay, so let me first start with introduce you to this idea of magic pictures. So what you should imagine is this is a type of puzzle. If you haven't seen them, when I was a school children, there was a monthly puzzle journal, and sometimes in the middle 2 pages were occupying, say, 7 or 8 of such magic pictures. Those were my favorites. When you go to the puzzle and you look at those pictures and try to solve the puzzle. So what is the puzzle? So let me show you a typical example of a magic picture. So what you see here is some sort of picture depicting some innocent looking themes, in this case some old Swiss mill. And then the puzzle is to find some pictures or figures of and it is told you what to look for. In this case, you might want to find some animals of various kind, faces of people hidden inside the picture. Somehow it is drawn with other things in the picture. So you could see perhaps here a horse or a donkey face, several faces formed from the rocks here, there, and something in the water. Then this would be the puzzle. Find 3 faces, 2 animals.
I don't even know what else is on this picture.
So this is a magic picture, but then there were a little bit more interesting ones. This is much more like the faces you can see on some famous toasts, or in the clouds people are claiming to see faces, so it's perhaps maybe random, not that interesting. So let me show you a different kind, which were much more to what I liked. So here, what you see in the picture maybe is a person in a coat is walking maybe by the Seine or something French looking anyway, by a tree. And what then you can search for, maybe it is told you that to look for a face. And in this case, and that's why I like this picture, the face is occupying almost the whole picture. So if you look at the picture, maybe half closed eyes, you will see a face showing, for example, the coat of the person is the nose of this person, is the nose of this face. You can see the 2 eyes, and the shape of the face is formed by the surrounding area. So these sort of things were really much nicer. It's a little bit out of the picture, it's much bigger. It's almost like you have one picture, which is the person walking by the river, and then another picture, which is the same as this one, but somehow this is completely different. It's the face of a person. So let me show you one more of these more traditional magic pictures, which is really going to pick the idea of what I really like about these magic pictures. And this is a historical, quite famous picture. It appeared first in a German humor magazine in more than 100 years ago. The question is asking which 2 animals are the most similar to each other. And the answer is the rabbit and the duck. So what you can see, of course, if you look at it from this direction, you can see the duck with its beak and its eyes looking that direction. But the exact same picture, if you look at it from the right and you think it's that now this is the mouth of the rabbit and this is the ears of the rabbit, then you can see a rabbit. So the same picture, the exact same picture, can show 2 completely different things depending on how you look at it. And this is the sort of magic pictures which are really attractive. So for example, I will show you in some mathematical context some of these magic pictures. We like them because if you want to, for example, study the ears of a rabbit, and maybe you haven't yet developed enough theory, but you have extensive theory about the beaks of the duck, then of course you already know what the ears of the bunny should look like. So that's the sort of idea of magic pictures in mathematics or even physics. We usually use the words duality, but it's the idea is similar. So let me show you one first example of a magic picture in the form of a game. So this is the game which has this, I must admit, not very attractive name. This is the 15 from 3 game. So let me explain the rules and then maybe we can play one game. So the game is going to be played between 2 players, and they play one after the other. One starts, then comes the other, and then the first one, etc. They play alternatingly. So when you come, your turn, then you will pick one of the numbers between 1 and 9, but you cannot pick any of the numbers which have been already taken. Maybe the numbers are in a bowl or something, and you are pulling them out one after the other. So this is just explained here. And then finally, just to understand the name of the game, you are going to win if you can make 15 out of 3 of your already chosen numbers. So that's the game, and in fact I usually start my courses in analysis and anything with a large audience, or playing around of this game with any volunteers from the audience. So this is the time now that I should ask for a volunteer who would like to play with these rules with me. So any volunteers? There will be prizes at the end. Someone wants to play just a quick, fast game because we are going to pick. Okay, sorry. We will be picking numbers. Okay, so Frederick is going to play with me. Just to be fast and for you to get to the rhythm of the game, I show you how it works. So I pick a number 5. Okay, and then it's your turn, and you should pick a number.
I have 3.
Okay. Then, okay, so I have 3. You have 3. The 3 is no longer available. And so then it is going to be my turn, and I pick number 9. Number 9. This is no longer available. So now you have to be
Okay, I have to pick 1.
very clever, very clever. So you are taking number 1. But then I am going to attack with number 2. And then it's your turn. Now I am threatening again.
Okay, so I have to take 4.
You have to take 4, but unfortunately you should also you should have taken as well 8.
Yeah,
Which I am taking now, and 2, 5, and 8, 2 add 2, 15. Okay, so I'm sure if you played another one, you would have fared much better. So let me go back now to discuss. So this is the good scenario, actually, what could happen in my class. I tell you later how this could happen that I lose, which is then going to become a bit embarrassing. Because the next part of this presentation is to explain a magic picture which will explain to us what was the game we were playing. And this is magic in another sense, because this other picture we have is a magic square itself. So if you look at this magic picture, then you will see this is a magic square. So this is a magic square using the numbers 1 to 9, and magic square means that the rows, the columns, and the 2 diagonals all add to the same number, which in this case is 15. And then now, if you have such a magic square, this will actually serve for us as a magic picture, because if you think about the game we played, we were picking numbers from 1 to 9. It's like choosing a box from this magic square, and then those who will collect 3 in a row, 3 in a column, or 3 on the 2 diagonals is going to win, and precisely those 3s are going to add to 15. So it's a special magic square in that regard too. So this then explains this picture. I'm showing you that this funny looking game, 15 from 3, is nothing but the game of tic-tac-toe. And so then you can now play the way how I played. So this was a little bit unfair with you, because I was on the side, I was doing these sort of things. I started with 5, which was a clever move, not just because it's the middle number between 1 and 9, but just because of that, it is the middle number in my magic square in the biggest number of winning positions. Then you took the wrong turn, you took 3, which is not that, but geometrically it's the same, so you took the equivalent turn of putting something on the side. Then I put something like this, and then I have a forced win, because you have to defend, and then I attack 2 different ways. And this was the same game actually what we played in some rotation. Okay, so this I hope gives you the first idea of a mathematical looking magic picture. You have a game which you can play with numbers, and then you can use your skills in number theory and algebra. And then you have a game which you can play geometrically on a 3x3 grid, and that's the same game. So, but depending on which direction you are looking at it, you can learn different aspects of the same game. Okay, so here is my winning move. So the problem, of course, is that if I let the student start 5 and then I do the same mistake putting next to it, and this happened once, and this is very embarrassing, right? Because I'm trying to explain to them how it's great to know geometry, for example, because then you can beat people in silly games like 15 from 3, but then I lose. So it was hard to talk myself out of that. So it's very good for this game to learn the winning strategy, and I rehearsed this time. Okay. So this was something I do in my classes, a magic picture, and then to relate to the main themes of this workshop, which are Higgs bundles. They all arise from equations in mathematical physics, or in physics, in fact. And so what I'm going to now show you some examples of equations in mathematical physics, and several of them there will be aspects about those ideas which also exhibit one version or another of a magic picture. So a magic picture also happens in one of the famous equations in physics with Maxwell's equations, which you can, I mean, many of you will have seen these sort of things. You can write in vacuum in this form. I'm, of course, picking a particular shape for the equation. And instead of explaining of what these things are, then how the equations are formed, I just use words, and then I will point out a magic picture in this equation. So the sort of things this is an equation for is an electric field, which in this case is a time variable electric field. Somehow it's an object which lives in 4 dimensions, and so is B, which is a magnetic field. And when you have such an equation, you can do 2 things, maybe. In this case, one, if you are more physics-minded, then now you can turn off or on the light, because of course these are the equations which describe us electricity. But as I was just pointed out today, in fact, there was like 50 years gap between the discovery of the theory and the application to electricity. The other thing, if you're a mathematician, then you don't necessarily care about electricity. You are just looking at the equation, and the way how it's presented already should show you that somehow E and B are almost interchangeable. It's like they are the 2 faces of the same magic picture. If you replace E with B, the 2 equations are almost invariant. Because of this minus sign, the actual magic picture here is the electromagnetic duality is replacing E and B with this extra sign. And so then the equations remain unchanged, and this symmetry of the equation actually leads to many deep facts in particle physics and eventually in mathematics. So let me continue with some equations. So now the aim of the next few slides, that in maybe some entertaining form introduce the equations, eventually Hitchin stability equations, which describes those Higgs bundles that we are making or living on, at least the participants of this workshop, or some of them anyway. So the whole thing for us starts from a generalization of the Maxwell's equation. So somehow Maxwell's equations is an equation with some commutative variable in it, and then you can make those variables non-commutative, and that's a really non-trivial extension of this, which was extremely important in physics, in theoretical physics, and later in mathematics. So I show you the Young-Mills equations in 4 dimensions, and it is quite easy to show to those who have this mark of the institute, because these Young-Mills equations are one example of the mugs you can get as a present from the institute. And so here are the equations. So the mug might cost a little bit, but you know that what you have in return may be worth much more. It is worth maybe $1 million if you can solve one of the minimum price problems, just to prove the mass gap exists in Young-Mills theories. So let me show you another mug, if you are doing mugs. This mug is going to have something which will make them physically even more interesting, and somehow even more money is involved. And that's the standard model of particle physics is building on theories which in big part using the same formalism as the Young-Mills equations. In fact, these Young-Mills equations are part of the standard model of particle physics. They can be, the Lagrangian of the theory can be conveniently abbreviated and put it on a mug, which apparently is the usual mug people at CERN are using. So at IMS we have some mathematically simplified things like the Young-Mills equations. They have the whole Lagrangian of the whole standard model. So actually apparently there are some mistakes on this, but I am not qualified to say. What you can notice though is that here you see somehow the Young-Mills fields, this familiar F letter anyway, and then you have 3 times a little phi, and that phi is our focus now. This is the Higgs particle. So it is one of the central parts of the theory of the standard model. It is the particle which is giving mass to all the others, and it is a really different one. One thing is that you write it with a different letter, like phi, which we will always do this in our field as well. In a Higgs bundle, we also have phi. The other thing is that this is a Higgs field, meaning it behaves differently than the particles described by the Young-Mills equations. So they are what we call scalar fields. They are like functions on space. The electromagnetic fields, they are not really functions. They change much more complicated way when you look at it in different coordinates. But the Higgs field is just something like a function. It's a much simpler object mathematically, but they also interact with many of probably all of the other fields. Okay, so then what you can do, you can be a mathematician like us, and then you can try to look at more simpler versions of the same Young-Mills equations. One thing we do is that we look at it in an idealized world when time becomes imaginary. And the other thing is we are looking at is the self-dual Young-Mills equations, but this is just aside. And once you do that, you can start to study solutions of the Young-Mills equations which are invariant by translations in one direction. Oh, that will be the monopoles, but I actually have a slide about the Higgs particle so that we actually can see that some of these Higgs things are existing in nature. And so, and I have to come back from this equation, and I come back to that later. So there was, of course, one of the, can you read this? Yeah. One of the famous achievements of CERN, not just for them to have such a nice mug, but also that they discovered this Higgs particle 2 years ago. And this was done by 2 parallelly run experiments. They are 2 major experiments done very far away on the 20 or so kilometer diameter collider, the LHC. They were not actually supposed to talk to each other, even if they were spouses, which apparently happened. And so they did their experiments independently, and they both found evidences of the existence of this Higgs particle. And so you can see many fantastic pictures. One of the pictures which shows you the discovery of the Higgs particle is the one from CMS, one of the experiments. And here what you can see, as I was explaining in CERN a month ago when we visited with family, you actually get a postdoc together with whom you can talk to 3 hours, because she was showing us around, and she was working at CMS, so she actually could explain what is this picture about. And so what you can see here is the result, what is called the Higgs event, and this Higgs event in particular was at the end of an experiment when they were colliding 2 beams of protons. So what they do, they accelerate to very high speed 2 beams of opposite going protons, and they capture them in their machine and try to see if they can record events, which means to see them collide. And when they collide, the theory says that the Higgs particle should be created, but then they are very short-lived. You will not see a Higgs particle. What you will see is the particles it will decay to. So in this experiment, the Higgs boson, which after it was created, very quickly after that it decays into 2 photons, which these 2 green lines are showing us. And similarly, paralleling the other experiment, you could see other Higgs events, and here I think, I just read this, I don't know what it means, that it's decaying the Higgs boson now to tau particles, and then the tau particles decay further to muon and an electron. The red apparently is a muon and the blue is an electron. Anyway, and then this is statistical, so surprising thing that she told us that now we can be 95% sure that there is a Higgs boson, and I said, what if the 5% is the true scenario? But she said that in physics 95% is a certainty. I couldn't understand that. But of course we are mathematicians, so. Okay, so now I'm coming back to that equation reduction I started to talk about, because I was carried off with the mathematical idea of looking at the Young-Mills equation, because I just have this copy in front of me. So the dimensional reduction of the equation reduces in an equation which is called the Bogomolny equations. Now it's 3-dimensional. Now the fields have 3 variables because we had assumed that one variable was independent. And then you have an equation like that again with the gauge field and some sort of Higgs field. And the solutions should be mathematical models for magnetic monopoles. So magnetic monopoles again are some hypothetical particles which were first proposed by Dirac to be able to explain that the charges that the electrons carry could be explained if there was ever existed a single magnetic monopole. Of course we haven't seen one because the magnets we see are always dipoles. You have the south and the north pole, and then no matter how you are cutting them off into pieces, all the pieces will still have the south and north pole, always dipoles, and single pole poles you never see alone. And in fact, if they existed, then they would have such a large mass that they could only have been produced in the very early universe, and the present theory is that maybe around the Big Bang they were created, and they therefore are reality. But this idea are really out of reach for discovery at the present level. But what I just found out researching about the experimental results about magnetic monopoles, that even though you cannot find a magnetic monopole in nature, you can actually create one, which they call a synthetic magnetic monopole. So this was somehow they recreated the mathematics of the Dirac monopole in an electric field. So it's not a magnetic monopole per se, but they managed to have a physical situation which is described by the same equations. And apparently you can even make a sort of photograph. So I can tell you, I don't even know what these things mean, but they found the magnetic monopole in a Bose-Einstein condensate in an ultra-cold rubidium. So I think it's easier to remember they found the magnetic monopole in a super cool metal. I think that's what it was really. But anyway, so it is a paper in Nature, and some sort of magnetic monopoles do exist. And so for us mathematicians, even though they might not exist, we can study the equations. So what we can do is that you can study the space of solutions, all magnetic monopoles which of a given type. For example, you can imagine studying 2 magnetic monopoles, their space and how they evolve with time. And then with a really beautiful mathematical theory and results, Otti and Hitching managed to completely understand the space of two magnetic monopoles and how they behave in low temperature. And based on their results, which for us mathematicians, it is understanding the metric or the geodesics on the metric on the moduli space of magnetic monopoles, they managed to understand how their magnetic monopoles would behave. And so they had this fantastic opportunity with IBM in 1988 to make a movie about it. And I cut out some parts so that quickly you can see the sort of things the movie is showing. So again, we are going to see the scattering of two magnetic monopoles based on analyzing very deep structures of the Bogomolny equation. So it explains one aspect of the scattering which is going to be shown. And then the two monopoles do their dance around each other. It's a really nice thing that these pictures are explicitly explained by understanding some Heiberg geometry explicitly. Then changing some parameters, you will see that the motion will be more and more entangled. And then one more, where they almost cannot get apart. But they are monopoles eventually, so they will get apart. Okay, so this was then some mathematics around the magnetic monopoles, and then this is the starting point for the discovery of what we are studying in this workshop, the so-called Higgs bundles. So the Higgs bundles were discovered by Hitchin, by Nigel Hitchin. I can show you, well, maybe not the place where this was discovered, but his office in Oxford. Here is Nigel in the oops. So here is Nigel in the middle. And then those of you, many of us in the conference or in the workshop were actually students of Nigel, quite a few of us. And then we would know this office quite well. So even though Nigel didn't discover Higgs bundles in this office, but to me this is a fantastic picture because this is where I learned about Higgs bundles. And then it turns out that the picture was taken by Sean Martin, who accidentally I re-met after, I don't know, 15 years here in Singapore. He's now based in Singapore. I always knew he was the one who made it, and back then apparently this was technically a less obvious thing to do than these days. But this is a fantastic picture. We have one thesis here. I'm sure those who are students of his, and many memorable explanations on the blackboard. Well, anyway, so Nigel was studying first the Young-Mills equations with Atiyah and Zinger, and they with Atiyah studied the Bogomolny equations with similar ideas, and then he was continuing with this idea of looking at the Young-Mills equations. First, for the Bogomolny equation, he wanted to see independence of one of the variables, and then in the Hitchin equations you will look at assumptions which are independent of two of the variables. That is their translation. And then what you get is the focus for us is the Hitchin equations. Again, this will be a solution is going to be a pair of objects, some sort of gauge field A, and together with the Higgs field, which is the analog Higgs field from the Bogomolny equation and from the actual Higgs field in 4 dimensions. There is a slight difference though, is that phi is no longer going to be just a scalar, it will be a bond form, but somehow the analogy is still there. Nigel did coin the name Higgs field for phi, and later Simpson called the pair of objects Higgs bundles. Maybe Hitchin pairs is also a used term, but somehow Higgs name became very famous, so somehow Higgs bundles stuck. And so here is already another magic picture you can observe in this theory is that to a solution of the Hitchin equation, you can either attach a Higgs bundle or you can attach, well, I just call it here a character. So what it is, of course, is a representation of the fundamental group of the two-dimensional surface where the equations take place. But you will see, I will show you some sculptures in a moment, that these two things, the Higgs bundles and characters via Hitchin equations, are really going to describe the same reality, but their geometry are really, really different. Even though the underlying topology should be the same, but several aspects are going to be different. So this is one more example of these magic pictures. We will be looking at solutions of Hitchin equation, and if you look at it from the perspective of Higgs bundles, you will get one geometry. If you look at it from the perspective of characters, you get another. And so in fact, this is the motto of our workshop. The modular space of all solutions turns out to be a manifold with an extremely rich geometric structure, and then only part of this two-faceted magic picture I'm talking about here. There are many other aspects which bring in more and more amazing richness into the theory. So this was in Nigel's original paper in 1987, where he introduced Higgs bundles, and since then many people have studied and discovered even more properties about them. So let me show you a result of a project. Actually, we started with Nigel. We were thinking about trying to make a sculpture originally for the New Institute in Oxford, and the idea was trying to make a sculpture about Higgs bundles. And so I'll show you a result of such a sculpture which you can make. So what you will see is the space of Higgs bundles, one space we are studying here. And then I have several of them 3D printed. So one thing which is nice that now that I can give it around and everyone can have one and study them, keep modular space of Higgs bundles in your hand. Yes. And so I have a bigger version just for demonstration purposes. So what you can see here, for the experts, it's explained. What you see here is at least topologically faithful version of the real points of the modular space of SL2 parabolic Higgs bundles on an elliptic curve. And so the sculpture was designed by me, but then I couldn't really program the computer graphics to make a sculpture out of that. And so I had to hire a professional, Olivier Labs. And so the nice thing now that in fact it's not just you can create them and print them out, now you can even look at them inside a PDF file. And previously we would only have abstract mathematical tools to think about the geometry and topology of these. But with these new technologies you can actually hold the modular space of Higgs bundles in your hand, and you can study at least the topology of its real points. And so what happened after this was very interesting, because once I got a big bunch of them to be back to Lausanne, then I put a picture of myself to Facebook to be proudly show at least some of these sculptures. And then there was a very interesting side discussion on Facebook about, so first of all, people wanted to get the STL file so that they can print some of them. In fact, some of these sculptures were printed across the ocean in Texas by Sean Lawton. And so that's why I call these teleporting Higgs bundles, because the actual Higgs bundle never crossed the ocean. It's just a file which went over there and Sean printed them out, and then you have them on this space there. But what also worked out in this Facebook conversation is that Sean was doing some of these similar 3D printing projects himself, and then he had one which he called monkey pens. So here is, it turns out to be precisely the character variety presentation of the same moduli space. So this is Sean's monkey pence. So it's the real points of an SR2 character variety. It's in the other box. So you can take another one and compare the two. And then we can look at this. It looks fairly different. Maybe the only thing for now which seems to be similar is that both seem to have 4 ends. And then at the end of this lecture we will be able to compare one other aspect of them. And then we will be able to somehow tell them apart, really, even topologically. Okay, so I have 20 or so minutes. And so this opens up the last section of the talk. I will explain how these moduli space of Higgs bundles showed up in a really unexpected part in mathematics. They were in fact used to do something relating to number theory. And the number theory which shows up is originally is the famous Fermat's last theorem. So for Fermat's last theorem, the origins go back probably at least to Babylon, almost 4,000 years ago. On this clay table found in the deserts in Iraq, you can see 15 or so lines, and then these turn out to be triples of numbers or even more information. So after a quick Google Translate, you can see the numbers actually there. And then of course now you can notice that these are of course just the Pythagorean triples of numbers. But in order to go there, you have to first know that they used base 60 and that they never used the decimal points. So this line is in fact the famous triple 3, 4, 5. Here you see on base 60, 3/4. Here you see 5/4. And then here you see d square minus u square is 3600 and its square is 60, which is 1 for them. So this is one of the Pythagorean triples. So this is amazing that almost 4,000 years ago, all these 15 lines were depicting in some convoluted way Pythagorean triples of positive integers. So these are ones which solve the equation of a squared plus b squared plus c squared equals c squared. And then based on that, in the early 17th century, Fermat produced, well, famously on the margin of a book discussing the Pythagorean numbers, a conjecture which in its original Latin looks like this. In fact, especially those who, I'm studying French, so it's actually not that bad to read. You can also use Google Translate, but then you will get something pretty awful. So, but then you probably want to go back to the Latin. But anyway, this really is just the famous statement that I have a proof, I have found the proof, but the margins are not wide enough to include it here. And then of course, he never written down the proof. Later he proved the conjecture, which I'm going to state formally in a moment, for n equals 3 and 4. So probably his proof was non-existent, or he forgot about this. He might have had the proof, but he just lost the piece of paper. So the theorem then says, which for a long time was just a conjecture, is that when n is bigger than 2, then there are no analogs of Pythagorean triples. There is no solution of the equation a to the n plus b to the n equals c to the n. Okay, so to show you one more example of magic pictures, I show you very roughly, how the proof of Weiss went to prove this Fermat's last theorem. So Weiss, of course, famously proved this almost more than 350 years later. This theorem, and his proof went roughly like this. So to a hypothetical solution of the equation, you can attach an elliptic curve. So an elliptic curve is just given by a cubic equation in x, so it's a degree 3 equation in x. A to the n and b to the n are some hypothetically existing numbers, so we put them here, and y and x are variables. So to this we attach this elliptic curve. Actually, the elliptic curves we can think topologically, the solution space are really just the tori's. I have a version of the tori here, which I really like to show for these opportunities. It's a swimming ring, but of course this is the torus, the solution slit. In fact, one point is missing, so you can imagine that this hole here is that one point which is missing from the torus. Then this is how it looks like graphically. And so then this magic picture, which was used very effectively by Morris to prove the non-existence of solutions of Fermat's equation, went like this. So it starts from an elliptic curve. So these are not just the torus, of course, it has this equation next to it, and to such an elliptic curve or an equation, you can attach something which is called a two-dimensional representation of the Galois group of a Q bar. And similarly, you can attach to this modular form. Not similarly, it's a different technique to a modular form, which is an object which exists in analytic number theory. You can also attach a two-dimensional representation of the Galois group. So to be more concrete, for example, to a modular form, you obtain a two-dimensional representation of the Galois group, and the corresponding elliptic curve will be this one. And so this way you are going to get a one-to-one correspondence between analytical number theoretical objects, modular forms, and elliptic curves, these cubic equations like this. And then it turns out that the Fermat curve, the one you hooked up from the hypothetical solution of the Fermat equation, cannot be modular. There cannot be a modular form where it comes from. And so if you have this magic picture which tells you that modular forms are the same thing as elliptic curves, then you can prove Fermat's last theorem. So this is one of the last magic pictures I want to show you. And in the remaining part of this lecture, I want to explain the topology which goes into both this, to explain this too, and also just to where the Higgs bundles will come in. So, okay, so then this is that number theoretical result which was proved with the use of Higgs bundles. And again, this is one other formula which is very important for this magic picture I showed you here. This can be greatly generalized to non-abelian groups, higher non-abelian groups, and then you get a technical result. That's why it's called lemma maybe, or it's a fundamental lemma. It's central in one part of this theory, and you get an equation like this that you need to prove. It looks quite simple. It in fact was called lemma because, for example, for SL2, this was understood to be computable by just looking at the combinatorics of a tree, like this, an infinite tree, and in fact this was really easily understood from the tree. And they expected that the similar statements for higher dimensional versions of the trees would be similarly easy to prove by combinatorial methods. But it turned out to be wrong, and people very slowly could just extend the result for SL3 and other groups. But it was much later by NGO to get the final result. Okay. So, to go there, there is one more problem we have to solve. And this problem is for toddlers, originally. This I found on the internet, and then this comes as your usual Facebook scan or on the internet. You can find the problems like this. Can you solve this problem which toddlers can solve in 5-10 minutes? Can you do it? And so here you see the problem, which is like this assignment question. What's the rule? How do you find the rule? In particular, what's 2581 is going to correspond to? And then I can let you, give you 5 minutes to see if you are as good as high school children, or we can do it together and quickly notice that there are many numbers here which use all the 4 numbers. like 1111 is going to 1, 0, 0, 0 is 4, 3, 3, 3 is 0, 6, 6, 6 is 4. This is always divisible by 4, so you can have a theory that maybe each digit is representing a number. So 0 then will be 1 because there is a 0, 0, 0 somewhere which is 4. So a single 0 should go to 1. Then 1, 1, 1, 1 is 4, 0, so 1 should go to 0. Similarly 2 and 3. 4 you don't have information because this is not listed on the left. 5 again goes to 0 because there is a 5, 5, 1 in the middle. I don't have here. This is the 5, 5, 5 goes to 0. Then 6, 6, 6 is also there. It gives you 1 because 6, 6, 6 gives you 4, etc. 8. Now you can do a little game, you can do a little problem, but here you see that there is 1 already, so 8 should give 2, and similarly 9 should give 1, and then everything works out. So this seems to be going down to the digits, and the only outstanding one is 4. So what would you think 4 should go to? 4 is not listed on anywhere in here, so you should understand the rule a little bit deeper than that. So what do you think 4 should go to? Anyone has a guess?
Well,
Very good. And why?
because I know the answer.
So anyone who doesn't know the answer, or he just discovered it himself. Okay, anyway, so of course, yes, 1, although 4 was not listed for a reason. So if you're American, you're from America, you would write 4 like this. If you are European, you might write 4 without the loop there. So indeed, the answer is 1 in this case, and the reason because this is the number of holes the number is creating. And so the number of holes for 0 is indeed 1. The number of holes in 8 is 2. And then finally we can answer why the two-dimensional representations of the Gala loop was used, because the answer for the torus is indeed 2. You have those 2 circles, which gives you these 2 holes on here. And so finally I can finish with the proof also of the fundamental lemma, or at least just give you a one slide ansatz, or just a summary. So this was proved recently by a Vietnamese mathematician, Gu Bao Chao. In 2010 he published the proof, and the same year he received the Fields Medal, and he might be, I think he's the first Southeast Asian mathematician to receive a Fields Medal, and he did very well with the Mathematical Olympiad. And in fact these days Asia is doing very well in the Mathematical Olympiad, so we might see more Fields Medals from Asia. And this proof in particular was really amazing, and then it was easily worth the Fields Medal. So his proof was only 160 pages. I'm saying only because Lagrange says in his review that it should have rather been 700 for people who are outside of the core of the subject to understand. And so what he was doing, just in these simple terms, he was identifying orbital integrals with the number of holes on Hitchin's moduli space of Higgs particle. So for example, you have the toy model in front of you, the one, and then the number of holes on it somehow is going to be one of these orbital integrals. And then he was really, to prove this identity of 2 orbital integrals, really had to do a lot of geometry, and one of the geometric constructions he was using is actually, and amazingly, is closely related to the electromagnetic duality in Maxwell's equations, which we had in the physics part. And so this concludes the proof, or the talk, not the proof. I haven't said anything about the proof, nothing about the 168 pages. But for the talk, let's just do this problem of counting the holes in these 2 models I have shown you. So we have the model, the toy model of the moduli space of Higgs bundles, and then the problem we have to face now is to count the number of holes on this. So any takers? So maybe you know the answer to this one. So we, of course, see two holes on the top of each. In fact, what you can see here is a little bit more than just the Higgs moduli space. You can see how these two circles change to another two circles at the other end. And somehow they go through a singular transition in the middle. And then if you look at the sculpture more carefully, you see that that transition in the middle is 5 circles. You have a big inner circle in there. I don't know how can I show it. It's these bigger circles and 4 attached circles. And then in fact, the whole picture does just retract, we say, to those 5 circles. And so indeed, the answer is going to be 5. So there are going to be 5 holes in here. And then you can compare it with the toy character variety, and you are going to see, even though both of them have the same number of ends, you have 4 ends, but this one, when you cut off these ending positions, which doesn't change its topology, will be a sphere where you removed 4 of the circles. So then if you think about this and you draw it on a plane, you will have a disk with 3 disks, smaller disks removed, and that will give you exactly 3 more circles. So the amazing thing for us who are in this program, we are always learn to think that the character varieties have the same topology as the Higgs moduli spaces. But in this example of the non-abelian Hodge theorem, what we see is that if we take the real points, which depend on the algebraic structure of the two, the topology of the real points is going to be different. So the surprising thing that the real points are different, but if you somehow complexify them, then these 3 here will become 5 somehow on the other side. So with this, I finish, and thank you very much for your attention.
Fascinating talk, but I think some very rather elementary stuff that we all know about magic squares to something most complicated, like Fédérale last year, Higgs Particle. And so I believe that Professor Hausel will be happy to answer questions. Are there any questions?
Isn't it so that the each one moduli, the real size has genus 1?
Is
Does it have genus 1? Looks like it has genus 1 if you can't all move out.
So first of all, so what is genus 1 is this thing, right? This is a genus 1. And this is moduli space of SL2 Higgs bundles on this.
From the figure, if I cap off all 4 ends.
You see an elliptic curve there? So I don't see how that's an elliptic curve. Could be, but you know this priorly? Or you just see that? I see. So the elliptic curve we see here are the real points of the elliptic curve are these 2 circles. So these 2 circles are the real points because I cut this torus in half, and then I do the reflection, and then the fixed points will be the 2 circles like this. So these 2 circles here are the real points of the elliptic curve, and then what you see is that how this elliptic curve degenerates into this middle configuration of 5 circles, which in the complex world are 5 p1s, 5 spheres attached to it according to the FID4 arrangement, and then it comes out differently on the other side. But to see that it's genus 1 is, I don't know. Yes.
What information do you need to build this?
So for this, the difficulty with this, I told you I couldn't do it myself, was that the algebraic equation which describes the family of elliptic curves doing this transition, I don't think can be embedded into R3 or into C3. And so what you can embed that equation to, you have to blow the R3 up 3 or 4 times. So what I was trying to do here is to understand this transition. So this is, by the way, the hitching vibration, for those who know what I'm talking about. So you have these elliptic curves, these are the fibers of the hitching net. In the middle you have the nilpotent cone. And then we just, originally Nigel, we were thinking together that what's this transition of the hitching net on the real points. And so what I was trying to do is to understand how the two circles degenerate into that nilpotent cone in the very middle. And so this is a topological picture of that transition. How algebraically this happens is harder, and this I couldn't put it in these coordinates. Yes?
Maxwell equation, when you solve the electric field and magnetic field, you get another sign.
Sorry?
The Maxwell equation.
Which duality?
The Maxwell equation.
Yes.
You solve the electric field and the magnetic
Yes.
field, get minus sign.
Yes.
So you solve again, you get 2 minus sign.
Right. But the equations are in that way, you can just pull out that minus 1. So yeah, you are right. It's properly speaking, it's an order 4 symmetry.
But actually it's order 2.
What's all that? Well, I mean, somehow the equation, if you put all the both fields minus sign, the minus sign you can cancel. But formally, there is an order for symmetry, but somehow in the summation level, it becomes an order 2 symmetry.
Well, if there are no more questions, let us thank Professor Hausel once again. I'd like to present to the speaker a token of appreciation. This is a pen holder from the Institute